Okay, so I'll start with the second lecture. I promised that today I was going to talk about Corseting Phenomena. So you will see what I mean by this. I guess that some of you know already about these problems because they are very classical problems of statistical physics and condensed matter and so on. But still, I think it's useful to discuss these problems in detail to be able to compare two dynamics of more curious or complex kind as the one of glasses that we are studying in these lectures. So I listed here a set of review articles, books, and references that might be useful for you to want to, if you want to go deeper into the discussion of Corseting systems. Well, you can get them later from the web page because the slides are already in the web page of the school. So the program for today's lecture is the following. So you see there are many points, but I'm not going to spend a lot of time on each of these points here. I just want to take you through the path that I think is good to understanding these sort of phenomena. And at the end, probably we'll not have time to tell you about some modern studies of Corseting problems. But if you are interested, you can go and look on the web page and see slides concerning certain studies that I have included over there, and then we can discuss them if you wish in private. So what about the Corseting phenomena? So I'm going to consider problems that are well understood. So for once, this is good. I will have a control parameter. Typically, it will be temperature over some energy scale. And this problem will have a phase transition at a certain critical value of this control parameter that separates two phases, a high temperature phase, which is typically disordered, and a low temperature phase, which is typically ordered. And the simplest example you can think about here is the problem of magnetic systems, but not spin glasses, just usual ferromagnetic-like materials, such that the order phase is ferromagnetic, the disorder phase is paramagnetic, and the critical point here is a conventional second order phase transition. Okay, so these are problems that we understand well from the static point of view. We understand the phases that characterize what the system can do as a function of a control parameter, and we also understand the phase transition, and there's nothing weird or complicated about that. But what we want to do is to start the dynamics of the system at an initial condition that is typically of very high temperature, and then quench the system, meaning that we are going to evolve it at a low temperature condition. That could be the critical point or could be below the critical point. So I'm thinking about what I sketched yesterday as the system coupled to the bath. The bath is characterized by some temperature T, and I'm going to prepare the sample at a very high T, and this will be the initial condition. And I'm going to do a quench instantaneously. Meaning that this initial condition I will evolve at Tc, or Ts, I called it Tc here, or at T smaller than Tc. Let me just erase this one here because it's nicer this way. Okay? So here I want to understand how the dynamics at the critical point can be characterized. And here I want to understand how the dynamics in an ordered conventional phase occurs. What happens? How does the system tries and evolves towards the equilibrium configurations that characterize the low temperature phase. So Yes?
Would you assume the coupling between the system and heat bath is like a very efficient, like an infinitely efficient?
Not infinitely efficient. It's just efficient. It's efficient enough to allow the system to dissipate energy and get rid, with some time scale, I mean, this you will see, try to get rid of the extra energy it has in its initial state compared to what it wants to have in equilibrium at the target temperature at which you do the evolution.
I'm just curious if there's a time scale or like a characterize the coupling effect and system and
Okay, that I'm going to today use only Markov evolution in the sense that all my baths today will be white baths, and they will not have any time scale associated to them. They will be infinitely fast in this sense. But we can discuss maybe tomorrow a little bit what happens when you use time delayed baths, in the sense that you have color noise or other couplings to the noise, which can be a little bit more complicated. Okay. Okay, so as I will tell you in a second, the dynamic mechanisms both at the critical point and below the critical point are very easy to understand and to visualize. But still there are some open questions that remain in this problem. And more than the open questions, I want to show you which are the scaling properties that we understand very well, and that we understand how they arise in these problems, and how later we would like to compare them to the ones that we see in more complex systems in which we don't know the dynamic mechanisms and so on. I mentioned here just a purely dynamical problem. Okay, this is not important for this lecture, but there are problems that mathematicians in particular like to look at that don't have an equilibrium Hamiltonian associated to them, but still they have some dynamic mechanism and some absorbing states they are called. Doesn't matter so much, but okay, I had it in the slide, so this is why I want to mention it very quickly. So the interests and goals of studying these problems are per se. They are problems which have experimental impact, so there is practical interest to understand them. They're situations that people like to look at in cosmology or in field theory that have to do with cooling through phase transitions with very slow procedures, so not infinitely fast as I do here instantaneously, but very, very slowly. So there's a lot of activity around that in other communities, let's say. From our point of view, it's a nice theoretical problem, and it also has perhaps some connections with glasses, or perhaps not, but we have to understand whether they are or they are not. So the setting is the same as said over there, system coupled to bath. So what does it happen? So I take an example, which is the simplest possible one, which is the two-dimensional Ising model. Okay? So I recall the definition here. I have Ising spins, plus or minus variables, and they are coupled ferromagnetically in the sense that J is positive. They live on the sides of a lattice, say a square lattice, and they are nearest neighbor interactions between the spins on this lattice. And I set the lattice in 2 dimensions because then it's easy to do plots, and it's also easier to do certain calculations, as you will see later. So which kind of dynamics should I impose on the spins? The classical spins like this don't have Newton dynamics associated to them, right? So I have to say what I'm going to use to update the spins in time in such a way that I want to mimic the coupling to the environment, right? So very quickly, I say here that the dynamics that is used to draw these plots is Monte Carlo dynamics, and then I will define it. But for the moment, just take it as some stochastic rule to evolve the configurations of the spins. And in these rules, temperature is implied, is involved, and I can choose it to be at the critical point of the 2D Ising problem, or I can choose it to be below. And I'm starting in both rows by initial conditions which are completely random. So the spins are sorry if I write here, but plus or minus 1 with probability a half in the initial state. This mimics a paramagnetic configuration at infinite temperature. There's no correlation at all between the spins on the sample. So I let the system evolve, and I see at later times, after the evolution, the snapshots here, and at an even later time, the snapshots over there. So what you immediately see from these plots is that there are regions where the spins tend to order. Let's look at the lower plots, which are clearer. So there are domains. These regions where the spins are all pointing up, let's say, that corresponds to red. It means that the spins are all pointing down, up, sorry, there. While in the white regions, they're all pointing down, apart from some perturbations, some fluctuations. You see here, there is one, there is another one, there is a white spot, and so on. So there are some reversed spins within the domains, but globally, I mean, from a coarse-grained view, they are all red here, and they're all white there. Okay. The process that takes the system from here to there, it's very clear that here the size of the domains is smaller than here. Right? If I more or less cross this figure with an horizontal line, let's say, and I look at the typical length of the intervals of one and the other color, well, here they are shorter than there. This is quite obvious. And if I let my system evolve further, I will see that they continue to grow, those domains. But there are domains of the two kinds. In this plot and in this plot, and in all subsequent plots, if my system size were infinity, they will be domains of the two kinds. Why is it so? Because in the ordered phase where I'm quenching to with this procedure, actually I have two equilibrium states. Two ferromagnetic equilibrium states which are equivalent from a static point of view, which is spins up or spins down. So what this means is that locally, when I do my quench, in this region, the system preferred to order in the up direction because of fluctuations, say that there were more red spins initially here, and they chose to pick this direction. However, here, it was the opposite. The surroundings of these spins which were here were mostly down, and then the system ordered here mostly down. So initially there is this equivalence, if you wish, of the two configurations of up and down spins that in different regions of space they are chosen locally with equal probability. I have to be up, I have to be down in this region, and then so on and so forth. This happens all over the sample, and in the course of time what will happen is that these regions of order will try to increase because the extra energy that the system wants to get rid of is quite clear that it's in the boundaries. Why? Because it's in the boundaries that these two values are different. So they give a negative contribution times the negative contribution here, it makes a positive contribution. So extra energy is concentrated on the interfaces or the domain walls. So I can put this here. So let's say, additional is not the word, but I don't find the good word. Extra, say. Because of the coupling to the bath, energy can be sent to the bath, and then the energy of the system as a function of time will go down, And this is done by erasing or killing these boundaries. And this is the main growth problem that we want to try to understand, or the coarsening problem is the other word that is used in the literature. Yes? For the moment, it's non-conserved dynamics. I will discuss, conserved and non-conserved separately in a second. Sorry?
For now, magnetization is not conserved.
For now, magnetization is not conserved. But I didn't want to define very quickly, the Multicolor Rule that I'm using. I will define it and make the distinction between the two in a second. The plots above are done at TC, and you see that the order is less evident, but there is some order as well. And basically what's going on at TC is that the system is growing patches of equilibrium at TC. And you know that at TC there are more fluctuations, and that on top of that the other parameter is 0 at the critical point. So there cannot be locally, when I look with a magnifying glass, there cannot be a magnetization being created locally in these growing patches. Magnetization should always be 0. But I have these structures of all sizes that start growing in my sample that are typical of the critical point. So the only difference from this point of view between this plot and that plot is that here I see the ordered phase, the ferromagnetic order phase, growing of the two kinds, and there I see, these all sizes of fluctuations also growing in the course of time. I have to grow the big ones, and these are the ones that are growing there. Yeah.
Does it mean that because the critical point is there's no scale? Scale is infinity or 0, so but it means it looks like some similarity.
Exactly. This I will discuss. There's also some similarity going on here of a slightly different kind, and we will discuss them in the talk. Okay. So there are other examples related to what Leo was asking, phase separation systems. So there, what happens is I have a mixture. I had already showed a slide yesterday. I have a mixture, and the mixture wants to separate and become, blue and white. And this is some example I got from the literature in biophysics. Or there is the phase separating glasses that I showed you yesterday. There are loads of examples. And the difference between the two will be in the microscopic rules that we will use, to update the variables, and that have to capture the microscopic mechanism for the dynamics, and this I will discuss. So theoretical setting, let me be a little bit more precise. I will use this example as a working example because it's simple. Of course, the easing problem is very easy to simulate with a computer, but it's not so easy to study analytically. So analytically, what is better what is much better to do is to go to a field theoretical description. So I think that perhaps Francesco talked about yesterday about coarse graining yesterday. So basically, reminder of statistical physics. What you do is you sum over the spins in a given box within the sample, and by doing this, you go to a continuous field, which is a scalar that depends on the position. So by moving over these boxes with central green points that I sketched over there, what you do is you go from discrete variables to a continuous field phi. Phi varies from -1 to 1. It's easy to see. The partition function, you can write it as a function of phi, a la Ginzburg-Landau. I'm just recalling Ginzburg-Landau for equilibrium. And this free energy functional of phi has a form which has, I want you to see this, an elastic contribution here, which is a term that counts energy when you are on a domain wall. Why do I say that? Because domain walls say that I look at this field phi along one direction of space. Domain walls will be given by configurations of this kind, where the field varies from one value phi naught to the inverse value minus phi naught in a continuous way. The domain boundary is here, or the domain wall, the center of the domain wall is in this position here. And this corresponds, say, to positive magnetization, the other extreme to negative magnetization. And it's clear that where the field changes is that this nabla, or this gradient acting on phi, is non-zero. And this term here is then describing the energy which is concentrated on this region of the domain wall. So it's a thing that you want to get rid of. And then the potential term, which is here, has this double well form. Well, my well should be identical. They're not in my plot, but sorry for that. So this is the potential of phi. This is phi. This is phi 0. And this is minus phi 0. Okay. So this is handy to use this continuous formalism because we will be able to do calculations with it. And in particular, the Ginzburg-Landau approach, what it tells you is that in the infinite volume limit, you can do saddle point approximation here, get the value of the saddle point, show that it's equal to the average of the field, that it's also equal to phi naught, get the free energy, and so on, and so forth. But of course, we are interested in dynamics, so we will use this formalism by adding a time dependence in a second. So these are the plots that I want to keep on the blackboard, so I will draw them here. So this is the free energy of Ginzburg-Landau. This is the form of the order parameter as a function of the control parameter. And here you have the second order phase transition, continuous in the sense that the order parameter is 0 in the paramagnetic phase and is non-zero in the ferromagnetic phase with the two branches which are completely symmetric, right? They are identical. Okay, one can generalize this problem to vector spins. No, sorry, before going to vector spins, I want to define the Monte Carlo rule. So in the formalism of the spins, the original one, I told you that I had to give a rule for updating the spins. So the usual Monte Carlo or Glauber rule for describing this ferromagnetic transition and problem is such that you always flip the spins if the flip takes you down in energy. You flip with a probability that is given by this Boltzmann expression if the variation is positive, and you flip with probability 1/2 if there is no change in the change of energy that you have with the proposal. So this responds or answers to Leo's question. Changes of neighboring spins which change the local magnetization are allowed by these dynamics. So you see here, for example, I can go from a configuration that locally has anti-parallel spins to a configuration that locally has parallel spins. So I'm going to from m equals 0 here to m equals 2, let's say, in the ending configuration. And this is allowed by these dynamics. And this dynamics is what is called non-conserved order parameter dynamics in the literature, because the order parameter is the magnetization for this problem and is not conserved locally. It's not only, it's non-conserved order parameter dynamics, and I should add also locally to make it more explicit still. Yes?
So I'm curious, why do we need to make this exception for equal energy case? Because without those, if you just
you can. You have certain liberty on how you choose this, the cases in which you don't change. Exactly. So it's better to include it this way. But you have some liberty to change that as well. Okay. The plots I'm showing are done with this dynamics. Okay, so this I said already. So you can also generalize to vector spins, and I show you this because I will show you some results for vector spins along the lecture, and this is just to tell you that. So now I have given you the dynamic rule for the spins. I want to give you the dynamic rule for the field, right? So the dynamic rule for the field will be Langevin dynamics. I will discuss in detail Langevin dynamics tomorrow, but just to introduce it here very quickly, there could be an inertia term. We will drop it. Why we will drop it in this context? Because it's not necessarily it is not necessary to keep it. Why so? Because all the times that are relevant in this dynamics are times which are longer than what I called yesterday the inertia time, which was m over gamma naught. So everything that has to do with the velocities, as I was mentioning yesterday, has saturated to equipartition values, and it's not relevant. So this one we can drop. Then there is dissipation, there is some deterministic force that has to be chosen, and there is noise. The deterministic force that we will choose it to be the variation of the, I didn't write it, Ginzburg-Landau free energy function that I defined before with respect to the field itself. So let me write this here, all this. Okay, so this is the equation with which one will work. I'm writing it for a scalar field. That is the one that comes from the Ising problem. And it can be generalized very easily to the vectorial case. Okay?
The two descriptions are equivalent now? Or
Sorry?
the two descriptions before and now are equivalent?
Okay, so here are the two descriptions, right? The discrete one and the continuous one. It depends what you want to look at. The continuous one is a coarse-grained version of the discrete one. So if you want to look at, in the discrete one, at the level of one spin, what is one spin doing, you will not have it in the continuous one. But when you are interested in large scales, so long distances and long times, then they are completely equivalent. And even more so, we have done some studies about distributions of domains and things like this, and they become equivalent at very short distances. I mean, you don't have to go very far away to make them equivalent. So in the end, they are equivalent. For all practical purposes, they are equivalent. So this is this is the summary, the free energy density, the Langevin equation here on the right. I mentioned this non-conserved other parameter dynamics. For the problems of phase separation, one has to deal with a different kind of dynamics, because if I make a mapping in which, say, upspin is blue particle, downspin is a yellow particle, and I want to represent the phase separating problem in terms of spins, now I cannot accept a movement in which I go from up and down to up and up, because this would mean blue, yellow going to blue, blue. This would mean killing a particle and creating another one. And this is not the problem I want to describe in the phase separation. I want to move particles around, exchange them, but not kill and create. So this necessarily makes the necessity of changing or considering other kind of dynamics as well, which are called conserved other parameter dynamics. and in the context of the spin problems. They go under the name of Kawasaki rule because he was the one who proposed how to generalize the updates to accept only exchanges of particles. So the only thing that you can accept is updates of this kind, where you exchange up and down spins only, but you don't accept this, right? So this means going from blue white to white blue, or white blue to blue white. Okay, and you can see that the conserved order parameter name is justified because here, if I think in terms of magnetization, this is magnetization 0, and this is still magnetization 0. So I'm not changing the magnetization with these dynamics. Now, these problems can also be generalized to have quenched randomness in them. How do you do that? Well, by considering interactions, J and J, which are not all equal. So just simply considering J and J's over there, which are drawn from some probability distribution. But let's say that we are only going to consider PDFs that have positive support. So, for example, I don't know, something like this. Okay? So this is 0. There is some mean, some width, but the support of this PDF doesn't go on the other side. So all the JIJs are positive, necessarily, but they can be different. So depending on how wide this distribution is, there could be more or less variation in the actual values of the JIJs in the sample. So this means that certain regions can be very, very ferromagnetic, and other regions could be less so if the values of the JIJs are small there. So there can be more tendency to ferromagnetism somewhere than otherwhere, and so on. Yes?
Why do we make the restriction that they're positive?
Because in this way, I'm not going to touch upon the spin glass problem in this lecture. Because in this way, the problem wants to be ferromagnetic everywhere in space, and there's not going to be frustration. So by this choice, there is no frustration. Where could I put it? Here. There is no frustration in the interactions. They all want to order the system in the same way. This makes the problem simpler. This makes what are called random ferromagnets, which are interesting in many respects, but not as complicated as spin as this. There was a question there, yeah.
Yeah, why is delta of 5 in the equation?
Delta of, it's a shorthand notation to write the variation of f with respect to phi. This here. Sometimes, yeah, this, I'm sure that Pierre will use this notation, Pierre Ledoussal, in his talks. Sometimes we use a label, a subindex like this, to represent variation in, in a shorthand way. Other questions? Yes?
So I understand this continuous equation is a good description of
Mm-hmm.
At the same time, how do we know that it is a good, good model describing the reality? In the sense that because for Hamiltonian dynamics, we exactly the force is exactly the gradient of potential.
Mm-hmm.
Here we're looking about the gradient of the free energy.
Right.
Cost gradient variable.
Exactly. So it's a proposal. Let's take it as a phenomenological equation that we will use and see what happens. Okay? It's true what you say. It's not a force, right? We first write down free energy as a function of a control of the order parameter, and then we say that we are going to take that object as an energy and take the variation with respect to it and construct a force. is not so obvious. But let's take it as a proposal and see what it gives, and then compare to what you obtain with the simulations and with the experiments, and see that it works fine. Leo.
Well, but you can also look at that equation and ask, what can you add to it? You can try to propose what would you add to it.
It's quite natural, no? So it's yeah. It's if you kill the noise, and it roughly does what you want it to do, because here you have this energy, elastic energy, that you want to get rid of, and this term is telling you by gradient descent that you're going to get rid of this elastic energy, and this term over here is fixing what are going to be the values of the constant pieces of other parameters. So it's chosen in such a way that the minima are at the values that you want it to be. So it's a construct on experience, let's say. Yes.
So I understand the rules about conservation and non-conservation, but you can also just do simple spin dynamics, right, in the icing model?
Here you cannot. In the conserved case, you have to do double spin dynamics. So you have to update 2 at a time.
What we gain is that we have transition space, or
No, it's just that here you're not breaking the conservation law that your system has, which is that you have to conserve the particles. You cannot kill them. You can just move them. So you have a conservation in your initial problem, in your physical problem, that you have to respect with your dynamics. And here, in the discrete version, you respect it with this Kawasaki rule. And the continuous version, you can also respect it by adding a Laplacian. I don't want to go into the details, but you can do it.
systems have this kind of conservation. I understand that if you have the ideal fluid or something.
Yes, exactly. This is just these mappings between particle problems and spin problems. So it's just a simple way of dealing with this particle problem in terms of using spins. And then for the spins, you have to change its dynamics to be able to conserve the number of particles of each kind. So this points to what's going to be important in the rest of my talk, which is that there are going to be universality classes in this problem. So I can announce it already now. They will depend on the dimension of the order parameter, so if it's a scalar, if it's a vector, whatever else it could be. But they will also depend on the conservation laws. Up to here, I'm like in standard static critical phenomena, in the sense that I also have universality classes, and the dimension of the order parameter plays a role in which are these each universality class. Here, I have to add the dynamic rule or conservation law to characterize these universality classes, as you will see arising a little bit later in the talk. Okay, so now let me try to discuss a little bit better these quenches. I don't know why there are those vertical lines there. Well, anyway, so at the initial condition, at infinite temperature, we have configurations like this, very disordered, where both the average of the spin or the average, should have written an average here, of the field are 0. In equilibrium, in, say, the positive magnetized case, I'm coming back to the non-conserved order parameter problem and the ferromagnetic case. Here, you have a positive value, let's say, with some fluctuations. So it's not 1, the magnetization in this equilibrium situation. It's a little bit lower than 1 because I'm working at finite temperature. There are some spins that are reversed with respect to the background. And the same for the field. And here I'm showing the critical temperature, where the other parameter is 0, because it's a second order phase transition. Okay? What I want to do then is, as I told you, go from the left-hand side snapshot either to the one in the middle or to the one on the right, depending on the quench that I do. So this I have already showed you. So I will have different kinds of dynamics depending on whether I quench to the critical point or to a lower temperature. And what I will show you is that the relaxation time, I'm calling it relaxation time and not equilibrium time, because I'm going to discuss the difference in a second. The relaxation time needed to reach the expectation value of the other parameter at the working temperature diverges with the system size when the system size grows. And this is like this. For all temperatures, I should have written 0 smaller than Tc here, because this is non-zero only below Tc. In the other case, I start from 0 and end in 0. But I will also see that at Tc, the time needed to reach all the characteristics of equilibrium at Tc also diverges with system size. So for all these problems, I will show you that the relaxation time, defined via this other parameter, is a function of the system size that diverges when the system size goes to infinity. And why do I distinguish relaxation from equilibrium? Because when I have the situation with the two possible equilibrium states, it's not enough to say that my other parameter arrived at phi naught positive, let's say, to have equilibrium. Equilibrium is actually the situation in which I can go from one to the other, right? It's a much longer time scale. Because in the Boltzmann distribution, these two states are equivalent. They have the same probability. They have to be represented in the same way. So true ergodicity means that if you do a plot of phi as a function of time for a given sample, it should do things like this. So this is T relaxation, where I have already managed to arrive at, say, phi 0. But then it should be able to reverse and go to the other side and go to minus phi 0. And then go back, and so on. This is a huge time. This is a time that will diverge with L in a much brutal manner, let's say, than the relaxation time itself. So for the moment in this problem, I will focus on this one. And I will show you how this relaxation time, the one needed to get here, behaves with L. And that will be done by studying how the linear sizes of equilibrium patches grows with time. That will be the goal. So this is what I'm saying in this slide here. So in both cases, both quenches to Tc or below Tc, I see the growth of these structures. And what occurs in these problems, which is not obvious, it occurs in other systems which are more complicated, is that in these problems, there is a single growing length that depends on time and the control parameters that characterizes how these patches grow, and that will give you a hint on what is this relaxation time by requiring that this growing length becomes of the order of the size of the system. Okay? But this is not the equilibration time, it's the relaxation time, and this is the difference I'm making here. Okay? Now, the universality classes that I was announcing here will be classified by how this R grows with time. classifies classes. It's not very nice, but this is what it is. Okay? So let me show you how this length can be observed, computed, measured. It can be measured by using dynamic scaling, and somebody mentioned dynamic scaling or scaling. Here it's dynamic scaling, but there is time involved in the issue. So what is done is to compute correlation functions. So let me define them here. So this is the equal time correlation function in the language of spins that one computes. So it's a function of distance between the spins, and it's a function of the time at which you measure. Time is always measured with respect to the initial time of the quench, and the distance, okay, is the distance. What do we know about this quantity in equilibrium? I will discuss this in a second. We know that at the critical point, this quantity decreases as a power law with the exponent that is written over there, so 2 minus d minus an anomalous exponent. This is the critical feature, that there is no exponential relaxation. It's a power law relaxation at the power law decay, I should say, at the critical point. So this is the black line which is shown in this plot over here. What happens if you do the quench? You let your Ising model evolve, and you measure the time correlation function that it's here as a function of distance for different times. So what you see is the different curves which are in this plot. Shorter time is the red, next the green, next the blue, and so on. So they're all very far away from the equilibrium curve, of course. They're approaching, but they're approaching very slowly. And if you go and look at, for example, how these curves evolve in time by just very simple evaluation, say that you look at when the correlation decays to 1 over e, at which distance it does decay to 1 over e at time t. So I'm cutting these curves with a horizontal line at 1 over e, and I'm looking at the point at which the curves cut this horizontal line. I can extract a first estimate of this growing length, which I can show, more or less see from the plots, that goes like a power law of time with an exponent. That I'm calling Zek here for equilibrium exponent. Why do I call it Zek? Because it turns out that if I compute, this can be done as well, the relaxation of an equilibrium configuration at the critical point, I will see that the same growing length characterizes this relaxation. So at the critical point, I can call this exponent Z critical, or I can call it Z equilibrium. Is the same. It takes some value, which is kind of non-trivial value. For example, for the 2D Ising model, it's something like 2.17, I think. It's like a new critical exponent. It's a dynamic critical exponent. That depends, as I said, on the dimension of the order parameter and the kind of dynamics that you use. This can, yes?
Why 1 over e?
It's just some estimate. You could use a half. You could use other ways of estimating by looking at scaling of those plots. I show you the scaling that I use later on, and you get more or less consistent results with always the same exponent. Okay? It's just the simplest possible way. Yeah?
This is full for the quench to the critical value.
Right.
Not
No, to the critical point here.
Otherwise, you cannot choose any value.
Otherwise, I cannot choose any value. Here, I cannot choose any value either, if I want to be very precise. But OK, I have a relatively wide window to play with. So dynamic scaling is an extension of static scaling, where instead of using the equilibrium correlation length to scale length, you use this growing length to scale length. Okay? So basically what you say, if you want to say it in words, is that at late times there is a single growing length, both at the critical point and below the critical point, that characterizes the typical size of your equilibrium patches, and that you can scale all correlation functions by using this single growing length. So for example, for the time-dependent correlation function that I have discussed before, what this means is that the correlations that I showed should scale like functions of distance, measuring distance, over the growing length. And two-time correlations should scale like ratios of the growing length measured at different times. Because here, there are times, but there are no lengths. So what you have to do is to measure times in terms of length and make ratios between them. Okay? Now, explained in this way, there seems to be no difference between critical quenches and subcritical quenches, but there is. And this is what I want to discuss now. And what it is that the main difference is that at critical quenches, the other parameter you want to go to is 0, while at subcritical quenches, the other parameters you want to go to is non-zero. So with the sketches, well, scaling, you know what scaling is. So this is a sketch of the meaning of scaling. I just jump over it. So what happens if I want to do the same kind of scaling for quenches to lower temperatures? I can look at the curves like before. I can do this cutting at some half height, let's say, and I will get another expression for the growing length, which takes the same kind of power law form, with a different exponent. And this different exponent is 2, independently of temperature. For all low temperatures is 2 in this problem. And this 2 can be shown with an argument that I will explain on the blackboard, but for the moment it's an observation. How do I see this scaling at work? And this is answer to also your question before. What we can do is take all the curves for different times that I showed before and try to put them together on a master curve. And how you do that? Well, you do it by using in the x-axis the ratio between the measuring distance and the growing length. For the growing length, you use t to the 1/2. And in the vertical axis, what you have, well, is the function, the master curve that makes collapse, or that represents the collapse of all these data. Okay? So this works well. Now I want to make the distinction between the critical quenches and the subcritical quenches more precise. For the moment, I only showed you this scaling for this part for the subcritical. I didn't show you that one for the critical, but I claim it can also be done. What is the difference between these two expressions that I showed here? The difference is in the prefactors. In the critical quench, you see that I write as a prefactor the equilibrium correlation as a function of distance. So the power law that is here, this power law, this is the equilibrium correlation at the critical point. While in the subcritical quench, this scaling function is multiplied by a constant, the equilibrium value of the magnetization at the working temperature squared, and the dependence on the equilibrium correlation function is additive. It appears here with a plus. Well, there's a times. Okay? Now, the limiting values of these functions f here and there are chosen in such a way that I match the two behaviors, the behavior, for example, of this term with this term, and the behavior of the product over there. So let me show you in a figure, in a sketch, what these things mean. Okay, I will do it on the blackboard because I draw it later. So what these things mean is that for the critical quenches, there is an envelope of your curves which should be given by this power law. Now I'm plotting in log-log scale so that the power law is a line. This is R. And the non-trivial factor that accompanies, that is together with this power law, is telling you that for different times, the equilibrium form is not reached yet, but it's approaching. So this is T1. This is T2. This is T3. Ordered such that T1 is more than T2, is more than T3, and so on. Okay? So, for longer and longer times of measurement, you will get closer and closer to the equilibrium correlation function, but you always have this going down curve that tells you that the system has not yet reached the equilibrium at Tc, and it's still time dependent, its correlation. And this is the correlation at long distances. And it's normal that long distances are not yet in equilibrium, while short distances have managed to equilibrate a bit better. So short distances equilibrate faster. Than long ones. Okay. So this is the scaling represented by the first line over there, and it's what you expect at Tc, because at Tc, the ending correlation function should be this one. And the limiting values of the function fc that I wrote over there is chosen in such a way that when time goes to infinity, the argument goes to 0. What did I do? Yes. The argument goes to 0, is here, and fc goes to 1. So you see, when time goes to infinity, the denominator goes to infinity. The argument goes to 0. I have to look at this limit. And in this limit, the function goes to 1, and the only thing is left is the dashed line here. Instead, when times are very short, let's see, when times are very short, what did I do? Times are very short, distance is very short. I think I made a mistake in that one. Yeah, this thing should go to 1. So, yeah, I think it's 1. This one here. So, when, where do I have 1? No, I have 1 in the opposite limit.
When the time is short,
yes.
I suppose that two particles with distance
yes.
are correlated. So the time goes to 0.
No, because at equal position, distance is 0, the spins are equal, this goes to 1. So the correlation starts from 1. So I made a mistake in the limit in here. That should be 1. Okay? So basically what I'm saying is that at distance 0, let me write it here. C, the total C, yes?
X equals 0.
Ah, you're right. Again, yes, it's true. It's true, it's true, it's true. You're right. So at x equals 0, little r is 0. The argument is also 0, and this is 1, and I have the good limit. Yes, thank you. I was making a mistake in my reasoning. Okay, so this is the description of the critical behavior of space-time correlation functions. Now what happens at... Oh, temperatures below Tc, let me write it here. At temperatures below Tc, I have to have, as a minimal decorrelation, I know that in equilibrium, the minimal decorrelation that can be is m squared. Why do I know that? Because, let me write it here. Cec of R is just this Si Sj, right? The worst we can do is to have uncorrelated spins, right? So uncorrelated spins means SISJ. There is no reason to have anti-correlated spins. So decorrelated spins means that I can factorize. If I can factorize in equilibrium, I insist, this gives me m squared in equilibrium. So this is the minimal decorrelation that I can have with this correlation function in equilibrium. So if I remember the drawings or the snapshots that I show you, where there were the domains and the fluctuations within the domains, these kind of plots here, or even this one, you see that there are some fluctuations within the domains. There are the domain walls, but forget the domain walls for the moment. At short distances, I don't see the domain walls. I just see what can happen within the domains. Within the domains, I am like in equilibrium with some thermal fluctuations due to temperature, right? I even have them in equilibrium, those. So what I expect to have for the space-time correlation function below Tc is that at short distances, this thing should behave like an equilibrium, go to a plateau at mx squared, and only later go down. But here, the other parameter is non-zero. So this thing is different from zero. It depends on temperature. And for different times, I will see things like this, right? Because at long distances, I see the domain walls, and I see that the spins decorrelate more than what they should in equilibrium. Yeah.
But the work parameters vary. Will also change temperature. Oh, no, this is time?
This is time. So this is at fixed temperature below Tc. So clearly, the plateau will move with temperature, because the equilibrium magnetization changes with temperature. But at a fixed temperature, I should see something like this, going to a plateau which has a fixed height, and then the departure with, again, different behavior depending on the times at which I'm measuring. Okay? So you see that the difference between this sketch and that sketch over here is that here the envelope, which is a power law that goes to 0, is due to the critical point, to the fact that the magnetization is 0 at the critical point. While here in equilibrium, I have this well-defined non-zero other parameter that gives me the height of the plateau. Yes?
This is not a glassy model?
Not a glassy model. It's a perfectly understandable problem in which you see what's going on from the pictures, and you can visualize the dynamic mechanism at work, and you can, with words, with your hands, understand the scaling. Exactly. So this kind of plot is very similar to what we learned for glasses. For glasses, I was showing, and also Ludovic was showing, plots of two-time correlations, but they're basically the same in form. So the other plots were showing T minus TW, and we were showing C of T, comma TW. But there was also the plateau, and the mechanism is the same. So in those cases, these were the TW1, TW2, TW3. In this case, we understand the origin of these curves. In the case of glasses, you can argue for the cages here and the structural relaxation later on. Here it's very clear. Here is the domain wall motion, And here is fluctuations within domains. Thermal fluctuations within domains. And in the previous plot, I showed you the scaling, why there was no, which one? This one. Why there was no plateau here? Because I did it at 0 temperature, this simulation. And at 0 temperature, the magnetization is 1, and this part is killed, right? This depends on temperature. So at 0 temperature, there is no first decay. This is why we didn't see it in this plot. But at final temperature, it should be there.
Can I understand that the average waiting time for the decay as like a domain, typical domain size, then it fluctuates and like wait enough time, so I have a probability of 1 that those domain just vanishes?
Yes. So what I want to do, if I have time, is to show how, for this concrete problem, one can compute below Tc the R of T that I wrote somewhere, the characteristic growing length. I don't know where it is in my should be somewhere. Here it is. So this one can be computed for the scalar Ginzburg-Landau problem with arguments which are relatively simple, and they are very nice to see at work, and they will explain what you asked me. Okay, so let me try to go a little bit quicker here. So the form of the growth now characterizes dynamical scaling, dynamical universality classes in the ordering phases. This I said already. So there are different ways to. Okay, let me jump over this. Let me go to this one, which is the answer to your question, actually, and then I'll try to do a calculation. Yes. Yes.
Do you see the crossover between the critical growth, psi, and then the domain?
Yes, you have to do, yeah. You have to be very careful, because you see the difference between the two exponents is so small, 2.17 against 2. You can try with the, sorry? In 3D it's a bit better, the difference, because it's, yeah, it's different. It's more different. But still, it's very difficult. It's very difficult to conclude. You can a bit better with the slow coolings that we did with Giulio, because there, you know, there's an effect of when you go through the critical point that you can see farther away, and then there you can get a little bit more convinced about the fact that the growth is different, you know, in close to TC and away from TC. But otherwise, it's exactly. This is 2TC, and the other one up there is below TC. Which one? This one?
Well, so you say there are two Z exponents. One is 2 and one is 2.17.
Exactly. So this is at TC for the two-dimensional Ising model, and this is for 2 and 3 dimensions below TC.
But it seems like there's 3 cases. You could have equilibrium dynamics and the Z exponent of equilibrium dynamics at TC.
Yes.
Then you could, and then you got 2 more cases quenching.
They're the same. This can be proven. Equilibrium dynamics at TC and quenching 2TC give you the same exponent. They do. Yeah, this can be proven with RGE, and so it's in particular explained by in the book by Tauber, but it's Roy Z and these kind of people Janssen who proved it.
And is there like an epsilon expansion or something?
Yes, sure. No, not for Z equals to 2, because you don't have any small parameter to work with here. So there are other kind of arguments that can be used to get the 2 below TC, but no RGE works. There have been some attempts, but none of them works really.
Some of it is going to the classic.
Exactly, yes. Yeah. And there are some self-consistent approximations that people have tried to work out as well, but they're not very good either. Yeah. Okay, so let me tell you a little bit how this zt equals 2 is obtained. But I will not go very much into the details, but just give you a flavor. So it's by working with the Ginsburg-Landau equation. So the Ginsburg-Landau equation, it's somewhere, but I repeat it here. And let me work at 0 temperature, where this noise is switched off, because it's simpler, and it doesn't change much for the purposes of what I want to say for the moment. So imagine now that you have that you want to look at this equation. So you want to look at this equation, and you see immediately that there are two solutions which are trivial, which is constant field everywhere equals to plus or minus phi naught, which are the minima of this potential. So this is 0, and then I set to 0 that variation over there. There is another solution which is a little bit less trivial, which is a solution for an infinite domain wall. So what I mean by this is say I work in 2 dimensions to make life easy, and I look in one direction of this 2-dimensional space, and I can construct a solution that looks like this. This is phi of x, independent of time, and it goes through, say, x equals 0 through 0. It goes from minus phi naught to phi naught at plus and minus infinity. And it has a form which can be derived for the 5/4 potential that gives the double well form that is over there, that it's like this. Well, put this in. So what is mu? Mu is the coefficient of the square term in the potential. So I'm working with this potential here. So this is the profile of a domain wall or a kink. People in high energy call it a kink. That tells you, how a domain wall behaves. Okay, so the G is in phi naught. Phi naught depends on G, and on mu as well. So I just put it at 0, but you could put it anywhere, of course. And how steep this thing is, it depends on mu. Because if you make the double well more thin and tall, the barrier, then this gets more steep. Okay. Now, what Allen and Kant did in the late 70s is that they expanded this equation around this solution. So this is a static solution, you can prove, if in the 2-dimensional space the domain wall is flat. So this is the x direction, but in the y direction it's always like this. Okay, it's not curved. So what I mean by this is that this is, say that this is plus and this is minus. The domain wall is situated at x equals 0 everywhere. So if instead of having a completely flat interface, you have an interface that is slightly curved, very weakly, you can use an expansion around this solution in this equation. I'm not going to go into the details of how you expand, but you can look at my notes if you wish. It's just taking care of partial derivatives in the direction of x correctly, and as a function of time also correctly. If you go ahead, what you find is that the velocity, say, of this point here, Why velocity? Because now, because of the curvature, the wall will not be static. It will start to move. Though the velocity will be perpendicular to the wall, and it will be proportional to the curvature of the wall here, at the point at which you are looking. Okay? So what they prove is that the, let's call it this way, x of t ex, so this is the velocity along the x direction in my notation, is proportional to the curvature times ex. And the sign is such that, my drawing is wrong, so the sign is such that the velocity goes in the opposite direction, actually. It goes this way. Okay? So it goes towards, imagine of a very large sphere, disk. It goes in the interior direction of the disk, the velocity. And this just comes from expanding around this kind of solution, this equation, and canceling terms and going ahead. Exactly. So what the dynamics is going to do is going to tend to round the interfaces. So I think here is the sketch. Imagine that at a certain point you have an interface surrounding a domain that looks like this one, the green one. The red arrows show you the velocity of points on the interface. So they point inwards, outwards, inwards, outwards. So in time, what will happen is that they will tend to become round, these domain walls. And not only that, what they will try to do is to collapse the domain walls. So somebody said that, you said that before. So what can be proven again relatively easily using this result is that you will kill, or the dynamics will kill the domains one by one, let's say. So let me do one very simple example on the blackboard, and then I can tell you how to generalize it. Imagine that you have a disk. I'm working in 2 dimensions because this is where the calculation is easy. With a radius r. The area of the surface, of this disk is pi r squared. I can take the time derivative of it. So this is pi twice r dr dt. But dr dt is the velocity I was talking about, right? Because I can sit here, and this is the velocity of this point that is pointing inwards, like that. So this is the v. So if I come here, I see that there is this 2 pi. There is a constant of proportionality that I'm not writing here, that typically one calls lambda, or I call lambda, over 2 pi, because like this I heal the 2 pi. And there is k. And there's a minus sign because I'm going inwards. Now, this k, what is it? For a disk, is 1 over r. So the r that I forgot here is cancelled. So then I have that dA dt is minus a constant. Doesn't depend on time. So this means that A of t is the initial value, say, of the EA when I started doing this calculation, minus lambda t times t. Let me call lambda squared, because this is the convention I used in the notes here. So now I see that this sphere in 2D decreases in time linearly. So I can say that its radius decreases in time like t to the 1/2. So I'm getting the 1/2 for one of these. But all of them behave in the same way, because if I want to see or imagine what is the space, real space structure of this problem, what is it? It's there. regions encircled by other regions and encircled by other regions, and the structure of domains is something like that. And at each time. And I looked at this kind of sphere over here, let's say, when I did this calculation on the sphere. But if I did it on any other form, because of the Gauss-Bonnet theorem in 2 dimensions, my result remains the same. We can prove it. I can show you. I mean, now it's late. I cannot do it on the blackboard. But you can obtain this for any form of domain. And actually, it's not domains I'm talking about here, because I can also do the same for an outer interface, something like this, that within has other domains of other kind. So this is what are called Hall enclosed areas. It doesn't matter so much, but the thing is that any structure that you look at encircled by or surrounded by a domain is decreasing in time with this same law, independently of its form. 2 dimensions. In 3D is a little bit different. But then, if everything is behaving like t, well, the only typical distance that I can have in my problem has to go like t to the 1/2. There is no other possibility, right? So this is an argument that gives you the 1/2 exponent for this non-conserved order parameter dynamics. Other questions here?
Is there like kind of like topological charge that's being conserved here?
There could be if you impose boundary conditions. So if you impose, for example, in my system, boundary conditions such that the spins have to be positive on this boundary and have to be negative on this boundary, then I will not be able to kill one domain wall. So the topological charge in this case would be 1 because I have one domain wall. So I have to impose them by the boundaries, the conservation of topological charge in this sense. No questions? Okay, so I said very quickly that, okay, what's the effect of temperature? It's just roughening the interfaces. It's not very important. It will change this prefactor here. So this is why this one I wrote as a function of temperature. So it's not that important. This is why there is no dependence of temperature of the exponents on temperature. So these are good exponents. They behave like critical exponents that don't depend on the details, depend on the conservation laws and dimension of the other parameters only. So let me jump over this and tell you very quickly that the exponent changes. So ZD is equal to 2 for non-conserved order parameter, is equal to 3 for conserved order parameter. And let me discuss the case of weak disorder, the random ferromagnet, because we're talking about randomness. So let's discuss that case. And then let's stop, although I had many other things to tell you, but anyway. So if I have quench randomness in the system, how can I imagine that quench randomness? For example, I gave you the example of the random ferromagnet, but maybe it's easier to draw the example of random fields. So imagine that you have impurities in your sample that are magnetic, they are very big, and they have spins that are frozen. So they impose fields on the other spins that are easy to flip. So for example, say that this one is up, say that this one is down, and then there is another up here, and there is another big down here there. And then there are other spins in my sample that they are normal ones that they can flip more easily. So I have drawn a configuration here that you see that somehow has a domain wall. Let's see. Let's try it like another one. This is down. So it has a domain wall that goes like this. So in the right I have more positive, in the left I have more negative spins, and there are these external things internal to the sample, but that they cannot be reversed, that impose fields which are negative here and fields which are positive over there. So it's clear that it will be hard for the domain wall to go to the right, right? But imagine that somehow everywhere else there's a situation such that the domain wall would like to go to the right, and that this region here would like to invade this other one over there. Because everywhere else, let's say that everything is down. So the domain wall here is pinned by this order. It's like attached to that position, and it's hard for it to advance. So, but it will advance, because the system would like to go and become negatively magnetized, let's say. So this situation one can think of as a situation in which you have your system in a metastable state, and you would like to go somewhere else where it's better. So there is a barrier to go across and take the system from here to there. Here. Okay? So the idea to estimate what is the time that the system will need to go above this barrier to the right part of my plot is the usual Arrhenius argument that tells you that, well, there will be some time scale and an exponential factor that depends on the height of the barrier over kBt, because kBt helps you to go above. The thermal fluctuations are going to be the ones that will depend this barrier. So this is what you have. Now, you have to estimate what's the value of this barrier. And the value of this barrier will be something that will depend on the length of the piece of domain wall that you want to move. So there will be a length scale here, let me call it R. That is the part of the wall or the line that you want to displace. So you can imagine that this will depend on this R. And how will it depend on this R? Well, you can do the usual droplet argument that tells you that when you will move the wall, you will win some free energy that will depend on this R, that will be typically proportional to some energy scale, energy density, times R to the D, the dimension of space, with a minus sign, because this is good. But you will pay some interfacial energy. I'm very crude with this argument, but you know, you do the typical thing of nucleation, and you say, well, this will be something like that. Then you look for the R that corresponds to the maximum here. If I think of this plot as being a reaction coordinate controlled by R, I get that R star goes like epsilon. How is it? It's yeah, sigma over epsilon, of course. Sigma over epsilon. I replace. I get that delta F R star goes like epsilon times this R star to the power D. Okay. This is the usual droplet argument. Of course, I'm not sure whether this works in the same way in the presence of quench disorder that I'm considering here. So in the presence of quench disorder, what you say is, okay, let's say that I still have a power law dependence with the radius, with the length, sorry, of this line, and that I just put another power. I don't know what this power is, but you know, so it will be a fitting parameter if you wish.
Should that be larger than D or smaller than D?
It depends on the. You can imagine that this thing has fractal properties, so then you can play with the fractal dimension of the region you want to go over, the line itself. So then you can have things like df over d here, for example. Okay, so in this way, sorry, this is not delta, this is the barrier itself. In this way, replace in the Arrhenius factor and you have r to psi kbt. And then you invert. I eliminate the a here, and I have that r should go like the log of t over t naught to 1 over psi, and then there is kbt in front. And there's an energy scale that I didn't write. It goes like that. Okay? So with this argument, you expect a much slower growth due to the pinning by disorder in this problem. Of course, in practice, when people simulate these kind of problems, first of all, what they have is that there is a crossover from a short time regime where the disorder has not started to be active, let's say, because there is local growth without taking care of pinning, because pinning is not very important at a local scale. I can always go around these things and create other with this distance and with this distance, and this I can do independently of these pinning fields. So what happens in practice is that at the beginning you see the power law of the pure case, which is the first line that I wrote over there, and only at very long times you should see this one, with a very slow crossover between the two. So people, when they do analysis of simulations, many times they just use an effective exponent, a power law that depends on temperature, that is just capturing the crossover between the first power law and the second logarithmic growth with just some smoothing via a power law. But one has to keep in mind that behind this weird exponent that depends on temperature now, there is actually this crossover between these two extreme regimes, very short times, very long times. Conceptually, that is what is going on. In practice, you can feed your data with something like this. But we don't like exponents that depend on temperature, right? We prefer that because we understand the two mechanisms at work, the one at short times and the one at long times. Okay, I think it's time to end here. Let me see what I had to tell you. Well, okay, you have planar magnets with other growing lengths. Oh, I didn't talk about many things. Okay, tomorrow I will continue then with the two-time responses. The other things I can jump over. I just tell you that these arguments allow you to get the growing length, R of t, the ones that I explained today, but they don't allow you to get the scaling functions, the form of the f's, below Tc. At Tc, RG arguments give you those. But below Tc is an open problem, which are the scaling functions. And tomorrow then I will pick up this discussion of coursing problems with the linear responses. It's going to be short. And then tomorrow it will be a bit more technical. I will do calculations on the blackboard. So, okay, this is what it's going to be. So beware. Beware. Okay, thank you.